Alright, so here in 11.10 we're going to introduce Taylor and Maclaurin series. So this will be a really big section that will cover a lot of new ideas. So the best way to take it all in is to try and practice as we go. There will be one definition that we'll rely on for almost all of the problems in this section. And so it's important that we practice this definition and get comfortable with it. But before we get to that basic definition, let's think about how we can formulate a Taylor series. Suppose the function f has a power series representation centered at x equals a. In other words, f of x here can be represented as a power series of the form c0 plus c1x minus a plus c2 x minus a squared, and so on, c3 x minus a cubed, and this of course would continue. And if I evaluate this series at x equals a, notice that all the terms that have an x minus a factor will become 0. So f of a is just the constant term c0. Which essentially that gives us a formula now for finding c0. So if I have a function whose power series representation is of this form, we know that that constant term must be equal to f of a. Moreover, if I were to take the derivative of this function, what would that look like? So then c0 is gone, and now my new constant term is c1. And the next term here, the derivative would be 2c2 x minus a, 3c3 x minus a squared, and so on. So f prime of a, now when I evaluate our derivative at a, leaves me with c1. And let's see, to continue this procedure, I'll work it out here for a couple more cases. Suppose I find the second derivative. That will be 2c2 plus 2 times 3c3 x minus a plus, then the next term would be 3 times 4 c4 x minus a squared, and so on. So then f double prime of a would just leave me with the constant term 2c2. Notice here that this would then give me c2 is equal to f double prime of a over 2. Let's see what the third derivative would be. So the third derivative would be 2 times 3c3. And then we would have 2 times 3 times 4c4 times x minus a. The next one would be, well, then the next term, which we haven't written here, would be of the form 4 times 5, c5. So when I take the derivative, it would be 3 times 4 times 5, c5, x minus a squared. Okay. And so here we see that the third derivative, f triple prime of a, is equal to 2 times 3c3. So therefore, c3 is equal to f triple prime of a over 3 factorial. Notice I'm putting 3 factorial in for 2 times 3, because that's essentially 2 times 3 times 1. Similarly here, 2 can be written as 2 factorial. Here, even though it's just c1 is equal to f prime of a, we can think of that as c1 is f prime of a over 1 factorial. And so we maybe notice a pattern here that all of the coefficients would be of the form the nth derivative at a over n factorial. So for instance here, if I were to go through and take the nth derivative of x, you would have something like n factorial cn plus, and then the next term would be n plus 1 times well, all the numbers going up to so it'd be 2 times 3 all the way up to n plus 1. Times cn plus 1 x minus a. And so we see that the nth derivative of f at a would equal to n factorial cn. And therefore the nth derivative divided by n factorial, the nth derivative at a divided by n factorial gives me the coefficient on the x to the n term. Okay, so all we've really done is we've shown that the power series representation of a function has all the derivatives are equal to the at a are equal to the derivative of f at a. And so here we've got the formula for finding the coefficients of our Taylor series. So if f has a power series representation at a, in other words something of this form, then its coefficients are given by the formula Cn equals the nth derivative at a over n factorial. Okay, and in fact what we have here is a Taylor series. So the Taylor series of a function f at a is given by this formula is the nth derivative at a over n factorial for each of the coefficients times x minus a to the n. And so here's the terms written out. It's f of a for the constant term, f prime of a over 1 factorial times x minus a, f double prime of a over 2 factorial times x minus a squared, f triple prime of a over 3 factorial times x minus a cubed, and so on. And in the special case, so this is called the Taylor series of a function of f at a. So in the special case when a is 0, it's called the Maclaurin series. And it has a form like this. It's the nth derivative at 0 over n factorial times x to the n. So it has f of 0 plus f prime of 0 over 1 factorial x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and so on. So this will be the formula that will give us all the coefficients of our Taylor series, or in this case the Maclaurin series. So let's practice this a little bit, see if we can get comfortable with using this formula to find the Taylor series of a function. Suppose I want to find the Maclaurin series of the function f of x equals e to the x and its radius of convergence. So we're finding a Maclaurin series. So we're going to be writing out the terms here. So f of 0 times f prime of 0 over 1 factorial, which is 1, times x, f double prime of 0 over 2 factorial, which is 2, times x minus a squared, and so on, f triple prime at 0 over 3 factorial times, and actually this one's centered at 0, so here I don't need the a, it's just x squared. So this one's just x cubed, and so on. So the next term would be the fourth derivative here, which I'll just write as fourth derivative at 0 over 4 factorial times x to the fourth. Okay, so the nice thing about e to the x, though, is that all its derivatives are going to be essentially the same, right? Because we know for f of x equals e to the x, and the derivative is e to the x, and the second derivative is e to the x, So all the derivatives are going to be e to the x. So in fact, the nth derivative here for any n is e to the x. So therefore, it's going to be e to the 0 for all these values that we're going to plug in here. So f of 0 is e to the 0 is 1, f prime of 0 is 1, f double prime of 0 is 1. So all the derivatives of every order at 0 is always 1. So therefore here we got a nice easy way to put in the values for f of 0, f prime of 0, f double prime of 0, and so on. So here the Taylor series, or actually I should say the Maclaurin series because it's centered at 0. Of e to the x is, well, we've got f of 0 is 1, plus f prime of 0 is 1 times x. F double prime is 1, so 1 over 2 factorial x squared. 1 over 3 factorial x cubed. And so on. 1 over 4 factorial x to the 4th. And so on. So now here is our power series representation of the function e to the x. Here I'll just write it in summation form. It's the sum from n equals 0 to infinity of x to the n over n factorial. Now a question is, we know that this is power series representation, but we might ask ourselves, for what values of x will this series converge? Is it convergent for all x? And if it does converge, what does it converge to? Does it converge to the values of e to the x? So these will be the next thing that we want to think about. Now that we have a power series that represents e to the x, does it converge, and what does it converge to? And before we do that, let's think about the nth degree Taylor polynomial of f, which is given by the Taylor series, but just going up to the nth degree term. So notice it's not the whole series, it doesn't go forever, it's sort of like a partial sum of a Taylor series. It only goes up to the nth degree term. So we call this Tn, or the nth degree Taylor polynomial of f at a. And let's just kind of look at what they look like here for this function e to the x. Of course, here's just the graph of e to the x, like we know it. And here's the degree 1 Taylor polynomial. Right, it's just the function 1 plus x. And we see it. What is it? It's really just the tangent line at x equals 1. Or sorry, at x equals 0. Here's the second degree Taylor polynomial. Notice it's a parabola. 1 plus x plus 1/2 x squared. Here's the third degree Taylor polynomial. And what we notice is that as the degree increases, the polynomials start to fit the curve more and more closely. So here's the third degree. Notice that in this vicinity around the center at x equals 0, the polynomial and the curve e to the x fit pretty closely. Here let's look at the fourth degree polynomial, Taylor polynomial. Notice again it starts to fit the curve more closely. And here's the fifth degree Taylor polynomial. Here's the sixth degree Taylor polynomial, and you start to see that, yeah, the range at which those two functions get are close to each other gets wider and wider with each term. And then here we'll go all the way out to the 10th degree Taylor polynomial, and we see it's just a little bit more closely fitting with the e to the x curve. And one thing we might ask is, well, how good is the approximation with the Taylor polynomial? And so what we'll look at here is the remainder term Rn of x, which gives us the tail end of the Taylor series. So it's like I take the whole Taylor series and I subtract off just the first n terms, so I subtract off the polynomial from up to the nth degree term, and what remains are the tail end of the series from the n plus 1th degree term on. And how do we know when f is equal to its Taylor series? Well, that'll be when that remainder term goes to 0 as n goes to infinity. So if the limit as n goes to infinity of r of n of x goes to 0, then f is equal to the sum of its Taylor series on the interval where it converges. So we'll explore this idea a little bit more in some subsequent slides.